Behavioral output follows predictable cause and effect mechanics. In any environment, these movements are governed by the laws of operant conditioning. The mechanics of reinforcement turn on two primary axes. The first determines the requirement for a reward, whether it is based on the number of responses emitted, a ratio schedule, or the amount of time that has elapsed, an interval schedule. The second axis dictates the predictability of that reward. A fixed schedule means the requirement remains constant, while a variable schedule means the requirement fluctuates around an average. These four variables combine to form the foundational operating system of behavioral reinforcement. Understanding these axes allows an observer to move beyond observing behavior to predicting its specific topographical pattern. This quadrant system maps the four basic schedules of reinforcement. In the first quadrant, a fixed ratio schedule provides reinforcement after a set number of occurrences. This FR5 graph shows a reward delivered after exactly 5 responses. This predictability produces a high response rate followed by a post-reinforcement pause, as the organism knows the exact effort required. The second quadrant shows a variable ratio schedule, like VR5, reinforcing after an average of 5 responses, meaning the requirement constantly changes. This unpredictability eliminates the pause. Because any response could produce the reinforcer, variable ratio generates the highest, steadiest response rate. The third quadrant illustrates the fixed interval schedule. On an FI 5-minute schedule, reinforcement is available for the first response after a 5-minute window elapses. This produces a scalloped signature on the graph, with responding accelerating as the interval's end approaches. Finally, the variable interval schedule reinforces the first response after an average amount of time, producing a moderate, constant rate of behavior without fixed pauses. These mechanics appear in common environments. Piece rate factory work follows a fixed ratio, slot machines utilize a variable ratio, checking for the mail at a specific time is a fixed interval, and waiting for a fish to bite is a variable interval. Identifying these response patterns is a baseline requirement for assessing reinforcement contingencies in a natural environment. Extinction occurs when a reinforced behavior no longer produces a reward. The duration a behavior persists without reinforcement is its resistance to extinction. The specific schedule of reinforcement in place before extinction begins dictates how long the behavior will survive. This chart ranks reinforcement schedules by resilience. At the bottom is continuous reinforcement, or CRF, where every correct response is reinforced. While useful for teaching new skills, behavior collapses quickly during extinction because the change in contingencies is immediately detectable. Behavior maintained by a variable ratio schedule is the most resistant to extinction. Because the organism is accustomed to unpredictable gaps between rewards, it continues responding long after the reinforcer is withdrawn. Reinforcing a problem behavior on a variable schedule creates a significant clinical challenge, as that behavior becomes highly persistent and difficult to eliminate. These mechanics are central to functional communication training, or FCT. FCT is an intervention where an individual is taught an appropriate communicative response, like using a picture card, to replace a problem behavior. This timeline illustrates schedule thinning, transitioning from a dense reinforcement training schedule to leaner, intermittent schedules of the natural environment. Monitoring behavior topography during thinning is vital. A post-reinforcement pause indicates a ratio schedule. A scallop indicates an interval schedule. If the reinforcement schedule is thinned too quickly, the individual may experience ratio strain. This occurs when the increase in the required number of responses is too large for the behavior to be maintained. Ratio strain often leads to a resurgence of the original problem behavior as the new communicative response fails to contact reinforcement. Skill maintenance is influenced by how a practitioner manages the transition through these specific reinforcement schedules. Natural environments typically involve compound schedules, which are combinations of 2 or more basic reinforcement schedules. These are chained schedules, where reinforcement is contingent on completing 2 or more basic schedules in a specific order. An SD is an antecedent stimulus that correlates with the availability of reinforcement for a particular behavior. On the left is a multiple schedule. This involves 2 or more basic schedules alternating, each signaled by a unique SD. In this example, a green card signals that an FR5 schedule is active, while a red card signals extinction. Because of these clear signals, the organism discriminates between the active contingencies and adjusts its responding accordingly. The right side shows a mixed schedule. The alternating schedules are the same as before, but there are no signals to indicate which schedule is currently in effect. Without an SD, the organism cannot identify the active schedule and responds based on an averaged reinforcement history. Providing or withholding an SD determines whether an individual will discriminate between specific environmental contexts or generalize behavior across them. Schedules can also be linked in a fixed sequence. Each link represents a task component. Completing one step serves as reinforcement for that behavior, providing the SD for the next. This is how complex routines are built. Completing one behavior, like putting on a coat, signals the next, grabbing a backpack, until the final reinforcer is reached. A tandem schedule follows the same sequence, but removes the SDs between each step, leaving the individual to complete the chain without external cues. Disruption to a single link in a chain schedule can halt the sequence, as subsequent stimulus control is lost. The final architectural arrangement is the concurrent schedule. A concurrent schedule involves two or more independent reinforcement schedules operating simultaneously. This allows an individual to choose between two or more distinct behaviors. The distribution of behavior in this scenario is a calculated mathematical process. This process is described by the matching law. The matching law states that the rate of responding across different options is proportional to the rate, quality, and immediacy of reinforcement provided. In clinical practice, the matching law is used to reduce problem behavior by ensuring that a therapeutic replacement behavior is on a significantly richer reinforcement schedule than the behavior targeted for reduction. Behavior goes where reinforcement flows. Mastering these schedules allows practitioners to accurately engineer behavioral change.